Kia ora Year 12 and Year 13. This is one last scholarship calculus video for 2018. I'm doing this one because it's in the paper that we gave out to Wellington College scholarship students last week. And one of my A-level students has asked me about how to do it. It's a really tough question. The whole paper was horrible. So if you're looking at this late, remember that things have got much better since then. But it's got some nice stuff in it, and he's asked me to have a look at it. So here we go. So we've got a question about a nautilus, and a nautilus is a marine creature, and the model for its shell is an equiangular spiral. We've got a picture of the shell here, but this is the diagram we're interested in. And these spirals have got equations of this form here. K is a constant, and theta is going to change as the spiral goes around, right? But we know that the radius, or the length from the origin out to the spiral, is going to get longer. Okay, so what we're interested in is that at every point P, the tangent to the curve makes the same angle alpha with the line from the point to the origin. Okay, so use the diagram, and we're told that the size of angle alpha depends on some number K. So the first part of the question is very, very doable if you remember what parametric equations are. So we have to use the parametric equations for the Cartesian coordinates of the point P in terms of theta. So we know that x is equal to r cos theta and y is equal to r sine theta. Okay, if you're looking at this point here, P, that's what's going on, right? And then we're going to use what we're given for r in here. We're going to use parametric differentiation to say that dy by dx is equal to dy by d theta times d theta by dx. Okay, I don't know how many marks that was worth, but that's what we'll do first. The second part is the part that Jim asked me about, which was what did the solutions mean and how did they do this bit down here? And I want to show you just one little Year 9 geometry thing that's going to make that problem doable. So let's do part A first. We've got r is equal to a e to the k theta. K is a constant. So what's x? Well, x will be equal to a e to the k theta cos theta. Y will equal a e to the k theta sine theta. We're going to differentiate each of those with respect to theta. So we're now back to a level 3, probably a level 3 merit question at this point. Straightforward product rule with parametric. Okay, so dx by d theta, I'm going to do this first times the derivative of this. So ae to the k theta times negative sine theta plus ka e to the k theta cos theta. Right, let's clean that up by factorising. ae to the k theta times, let's see, which way am I going to go? K cos theta minus sine theta. Now we're going to do the same thing for y. So we're going to differentiate this one. Oops. dy by d theta, same again. This times the derivative of this, then vice versa. Okay, so that's the first bit done there. Right, what's dy by dx? Well, it's dy by d theta times d theta by dx, which is just y dot divided by x dot, if you like that notation. So putting that together now, we get ae to the k theta times cos theta plus k sine theta divided by ae to the k theta times k cos theta minus sine theta. Right, now I'm going to manipulate this a little bit. Obviously we can divide through here, both of those are positive, and that leaves me with cos theta plus k sine theta over k cos theta minus sine theta. Now, I haven't got the schedule right in front of me, but I'm pretty sure that you'd get full marks for that part of the question if you went that far. Just having a look. Yeah, it says either form of dy by dx will be accepted. But you might be looking at those sines and cosines, and you might go on to the next part of the question, and somehow you want to use this result, right? Because the magic word that they've given is hence, right? So in here, they've said hence or otherwise, find the value of alpha in terms of k for this model. So what we want to be doing now is somehow working out how is the alpha linked up to the k. Right, so what I'm going to do before I get into B is I've got cosines and sines. I'm thinking about tan when I've got cosine and sine. So I'm going to divide everything through by cosine. And that'll give me 1 plus k sine theta over cos theta over k minus sine theta over cos theta. So this gives me 1 plus k tan theta over k minus tan theta. Okay, so that really is the end of that first part. Now I'm going to go back to the question for the second part, which is definitely the trickier bit. And now we're told, hence or otherwise, find the value of alpha in terms of k for this model. So we've got quite a nice expression for dy by dx. This is alpha up here. I've done the diagram bigger on the next slide. The marking schedule is not exactly detailed. What we're trying to do is to say, well, we've got a result for dy by dx. And our result for dy by dx was this. 1 plus k tan theta over k minus tan theta. We need to somehow figure out what alpha is. So we can't get alpha directly. This angle in here, this is alpha. But we do know something about the gradient of any curve. So if I've got just a straight line, and I know that this line has got derivative of dy by dx, I'm going to put in some parallel lines. So if I know the slope there, that's going to be the same as the slope down there. I don't have parallel lines in this problem, but what I do know is the value of the tangent here, we'll just call it m, is the same as the value of the tangent all the way around that line. So if we can figure out this, maybe we can find a link between this and something to do with alpha. So if we could delete that curve, the spiral, we might be able to figure out what's this angle. So go back up here, this is alpha here. This angle is vertically opposite, right? So this is year 9 geometry. This is vertically opposite. This one's theta, this one's alpha, right? Remember what we're saying is we've got the equation of a straight line, so the gradient's the same everywhere. And the gradient of that line is this thing here. So this angle in here is the exterior angle in a triangle. Or you could do 180 minus alpha plus theta here if you're having a really bad day. And then you'd see that this angle must be alpha plus theta. Right, so we're just about there because the gradient is tan of whatever angle's formed in here, right? So this is tan of alpha plus theta. But now we know that this is equal to our dy by dx expression. Okay, so that's the really tricky step. I don't think I would have seen that when I was 17. So, you know, if you see that, that's brilliant. But I'm going to go through it now to the end. So dy by dx was equal to 1 plus k tan theta over k minus tan theta. And that's equal to tan of alpha plus theta. Now, why do I like that? Well, I was asked to figure out a link between alpha and k. And I can now very easily apply my compound angle formula and do some work here. So we're going to have 1 plus k tan theta over this. So tan alpha plus tan theta over 1 minus tan alpha tan theta. Let's cross multiply and see what we get. So 1 plus All right, what we're looking to do now is basically back to level 2 algebra. We're going to expand everything. Hopefully some stuff's going to disappear. And then we're going to collect up terms that have got alpha and terms that don't have alpha. On the right-hand side, I get k tan alpha minus tan theta tan alpha plus k tan theta, oh, I've done that in a stupid order, minus tan squared theta. I think that's all right. Now we're just going to go through and underline some stuff that's in common on both sides. I've got a plus k tan theta here and here. What else have I got? And I've got a take away tan alpha tan theta here. So things are disappearing. I've got 1 minus k tan alpha tan squared theta is equal to k tan alpha minus tan squared theta. I'm going to chuck all the stuff with alpha onto the right-hand side. 1 plus tan squared theta is equal to k tan alpha. I've done something wrong. Oh no, plus k tan alpha tan squared theta. So now we have 1 plus tan squared 1 plus tan squared theta is equal to k 1 plus tan squared theta times tan alpha. That gives me 1 plus tan squared theta. Now I can divide through that by this because this will always be positive. That gives me 1 over k is equal to tan alpha. I should have written in there that it's always positive, but I'm running out of time. And now I've got alpha is equal to tan inverse of 1 over k. So there you go. That's the whole of that pretty awful question done. And as I said, tomorrow is all about part marks. So it's just about keeping your eye on and trying to spot stuff. Thanks for watching, and very best of luck for the exam.